So in this lesson, we're going to be working with exponents and dealing with some awkwardness that comes with exponents. Here's a whole bunch of exponent rules that you've already seen before, where, for instance, we know that 0 to the power of anything would be 0. Because, of course, if you do 0 times itself, however many times it is, you end up getting 0, because 0 times 0 times 0, 0 times anything is 0. We also have learned before that anything to the power of 0 is 1. Also, some infinity rules. Infinity to the power of anything, like infinity squared. Well, that would be infinity times infinity. And infinity times infinity would be infinity, so that's why we get that. 1 to the power of anything is 1, because 1 times 1 times 1 times 1, doesn't matter how many times you say times 1, you get 1. And then one last one here is, what about anything to the power of infinity? So like 2 to the power of infinity. Well, if you multiply 2 times 2 times 2 times 2 an infinite number of times, you end up out at infinity. So those are all rules that we know and that are fairly stable to be able to use. But there are some indeterminate powers that come along the way, and ones that when we end up dealing with limits, as you're going to see, can give us different results. And so we end up taking a look at these as our indeterminate powers. We have 0 to the power of 0. That's unknown, because remember, 0 to the power of anything was 0, but anything to the power of 0 is 1 as well. And so there's a little bit of conflict we got to resolve there. Also, if anything to the power of 0 is 1, but infinity to the power of anything is infinity, what's infinity to the 0? And finally, 1 to the power of infinity, what's that going to give us? And so let's go ahead and take a look at one example problem here for our lesson. We're going to use this one problem here to be able to see how this sort of thing can play out when we end up with that type of situation. Now, the first thing that we should do is we should actually just try direct substitution. So let's actually just plug that 0 in for x and see what we get out of it. So we're going to end up getting 1 plus sine of 4 times 0 to the power of cotangent of 0. So that's going to be 1 plus sine of 0. Sine of 0 is 0. And then cotangent of 0. Cotangent is cosine over sine. And that would give us 1 over 0, which in the context of a limit like this tells us that it's approaching infinity. So that actually ends up giving us infinity there. And so this problem ends up working out to be 1 to the power of infinity, which you might think, oh, well, wouldn't that just be 1? Not necessarily. It's at least certainly not in the context here of limits. And so because we ended up with an indeterminate power, that tells us that we're going to have to use some other rule here, specifically L'Hopital's rule. But in order to get to L'Hopital's rule, we have to end up having a fraction, because I need to be able to take the derivative of the top and the bottom of a fraction separately. But right now, I just have a function to the power of a function. Well, the first thing we're going to want to do there is we want to be able to get that exponent out of the exponent. To do that, we're actually going to need to be able to do an operation of both sides of this expression. Right now it's just an expression. We need it to be an equation. So we're going to go ahead and call it y equals, so that we actually can then figure out what it is as an equation. So we now have two sides, so we're keeping it balanced. And in this case, notice in order to do that, it has to be the limit of y. So that same limit that we had over here originally also has to be over here on the left side. All right, now, the reason why we did that is because in order to get an exponent out of the exponent, we can use logarithm rules. In this case, that means I'm going to actually want to take the natural log of both sides of this equation. When I do that, notice it's the limit of the natural log of y equals the limit of the natural log of what I originally had over here. The whole point of doing that is because now I know from my logarithm rules that this exponent can be pulled out front of the logarithm. And so I make that my next move. Already, we've made some ground. We got rid of the exponent. Now we have a product. Well, remember the last type of indeterminate forms we looked at was indeterminate products. And so that means that I'm going to try to take my product here where I have cotangent times the natural log, and I'm going to want to write that as a fraction. I have two options about how I go ahead and write that fraction at this point. I could write it as cosine of x times the natural log on the top all over sine, because cotangent is cosine over sine. Or I could alternatively write it as just the natural log of the same stuff over tangent of x. Either one of these can work, but in terms of knowing that I'm going to be finding the derivative of the top and the derivative of the bottom separately, this looks a lot easier to find the derivative than this, because I'd have to use product rule if I have cosine times natural log. So I'm going to go with this version here. So now that I've written it as a quotient, I now can finally use L'Hopital's rule, where I figure out the derivative of the top and the derivative of the bottom of my fraction separately. And you'll notice throughout this whole process, this side has stayed the same. Do not get lazy and just leave it out. Otherwise, it's going to bite you at the end, because we're actually going to need to come back and account for it when we're all done with this. But we still got to finish this part out over here. So I've now taken the derivative of the top. So the derivative of natural log would be 1 over whatever is inside of the natural log times the derivative of that inner function. So we're using chain rule in order to be able to get that. And then we do the derivative on the bottom as well. The derivative of tangent is secant squared. Now that I've done the derivative of the numerator and the denominator, I'm going to try direct substitution again. So I'm going to take the 0 that I'm approaching here, and I'm going to plug that in for x wherever I see x appears. So up here, when I plug 0 in for x, I'm going to be doing cosine of 0, which is 1. And so then 4 times 1 will give me 4. And then I'm going to be doing 1 plus sine of 0. So that's going to be 1 plus 0. So that's just 1 then. All right. And then that is all going to be over secant squared of 0. Secant squared, remember, secant is 1 over cosine. So 1 over cosine of 0 would be 1 over 1. So that just equals 1. And 1 squared then would be 1. So I do direct substitution, and I get 4 over 1 over 1. So I do 4 over 1 first on the top. That gives me 4. And then that 4 over 1 would equal 4. All right, so this is all boiled down, but the answer is not going to be 4. And remember I was saying that you need to keep track of that limit of the natural log of y on the left side? This is why. We need to get this to the point where we just say the limit as x is approaching 0 from the right of y. We don't want the natural log over there anymore. So we now have to get rid of the natural log so we can just know what the limit of y is. Well, how do we get rid of the natural log? Two ways you can think about it. One way is you just switch forms, so switch from logarithmic into exponential form. Or you can also think of it as we're taking e to the power of both sides. Because if you do e to the power of natural log of anything, the e and the natural log are inverse operations of each other and just gives you whatever is left. And so that means I'm going to do e to the power of both sides, which gives me e to the 4th on the right side, rather than just 4. This then is my final answer, because it's told me that the limit as x is approaching 0 from the right of y, where I defined y to be this function, is e to the 4th. And so you can give this answer either just by saying it is e to the 4th if you want to give it an exact form, or you could actually do e to the 4th to figure out what that would be as a decimal equivalent. This is now the process that we need to have down for doing this type of a problem. The first thing we did was we tried to find the limit using prior methods. The only one that would even have a chance here of working was direct substitution. And so we did that. We plugged in the 0 at the start, and we saw that it gave us an indeterminate form. And so that told us that we had to use something else. We had to go to L'Hopital's rule. So in order to use L'Hopital's rule with this type of problem, we first wrote the limit of y equals on the other side. Then we took the natural logarithm of both sides. That got us to the product. And so then this set of directions is exactly the same as what we did with our indeterminate products, where we write our product as a quotient. You'll notice a little note here, because there will always be a natural logarithm involved with these problems, put the natural logarithm on the top of your fraction. Then we use L'Hopital's rule. So we figured out what's the derivative of the numerator and what's the derivative of the denominator separately. And then once we did that, then we did direct substitution again to be able to figure out what that limit was. But we still had to do e to the power of both sides to get rid of the natural log on the left side. And so this is going to be your general process anytime you end up with an indeterminate power type of problem.